Hello students, now we're looking at quadratic models. So this fits in with section 6.3 in your syllabus. We're back to quadratics and this time we're looking at the models. And often with modeling, what we're going to be looking at are things like area, profit, and projectile motion. So let's start with an area example. So we've got a rectangle A, a fixed width of 0.5 centimeter, variable length of x plus 4. So we've got a width and a length. B has two varying sides. One is 1 minus x centimeters and the other is x minus 6. So we're going to start by sketching our two rectangles. So rectangle A, something like this. All right. So this is my rectangle A. We know it has a fixed width of 0.5 centimeter and a variable length of x plus 4 centimeters. So notice that x is not the length, x plus 4 is the length. So if I think about the area of this one, so my next thing says write a formula. So I'm going to start by putting my formula here. Area of rectangle A is 1/2 times my x plus 4. So my area is going to be centimeters squared. I could multiply that out and get 1/2 x plus 2. So I know the formula for this area is going to be a line. So the area is going to change constantly as x changes. For rectangle B, all right, so let me put in a better line here. All right, so rectangle B has two variable sides. One is 1 minus x, and the other one is x minus 6. So the area for rectangle B is going to be 1 minus x times x minus 6. And this one I'm not going to multiply out because I see it's a quadratic in root form. So C tells me to graph my areas. So my y-axis is going to be area, which I measure in centimeters squared. And my x-axis isn't length, but it's how this variable x is changing. So this is just x and it's measured in centimeters. But it's not a length on its own. So if I think about graphing this line for area A, I have a y-intercept of 2, and then my slope is 1/2. So I go up 1 over 2. So up 1 over 2. I could also think about going down 1 over 2, down 1 over 2, other way, up 1 over 2, up 1 over 2. So let's connect those with the straight line. All right, this is area A. For B, I've got my quadratic, so I've got an x-intercept of 1, an x-intercept of 6. I can see that halfway between those is going to be 3.5. That's my axis of symmetry. So if I want to find that y-coordinate, my y-coordinate is going to be 1 minus 3.5 times 3.5 minus 6. And I get 6.25. So here's 6, that's 6.5, so 6.25 is about here. And I'll draw my parabola, trying to make it smooth. All right. So knowing that this is area, I shouldn't have even drawn this bottom part down here because I know that area is positive. I'm going to come back up and draw this. Okay, so there's my two areas, and I'm stopping it here because I know that this is area B, and I know that area is positive. Same thing here. I don't go further because I know area is positive. But this one could keep going up. And I'm going to use that to help me with D. So D says determine a reasonable domain for each function based on the context of the problem. So the context of the problem here is area. So we know that area has to be positive. Or it could be 0. For rectangle A, the domain must be greater than or equal to -4, because that's when my y values are positive. For B, I only have positive area between these two values, which is 1 and 6. So 1 less than or equal to x less than or equal to 6. So those are the two places that my area is positive for each picture. Using my graph or otherwise, determine the values of x for when the area of rectangle A is greater than B. So I want A to be bigger than B, but also within my domains established. So I can see that A is bigger than B for all of this because rectangle B is going to have negative area, but negative area doesn't make sense. So I can only look at this region where rectangle B exists, because rectangle B doesn't exist outside this region. So within this region, where is A greater? Well, at this point, I can see that this area is greater than this small area. So it must be here, and also A is bigger over here. So I need to find these points of intersection. So I've got my points of intersection. I can do that by using my calculator to find the points of intersection. So we have half x plus 2, or we have 1 minus x times x minus 6. And we know our window, we're looking really at this area from 0, let's go up to 8, and we could say our max goes from 0 up to 10. So if I look at this graph, there's my line. Oh, or not. All right, so you know how to do that with your calculator. I've got it over here on Desmos, so I can look at my points of intersection. So there's one, here's my other. So my area for A is going to be bigger than B between this region, from 1 up to the 1.649. It's not greater here. So when I'm making that domain, I'm going to think about, so this point here has an x value of 1.65. So 1.65, 2.83 was the first point of intersection. The second point of intersection is 4.85, 4.43. So my x values are going to go from 1 to 1.65. I'm going to include the 1, but not the 1.65, because A is not bigger here. It's equal to, but I don't want equal to. It said to determine the values of x when the area of rectangle A is greater than B. So the second region is going to start at the 4.45, be less than x, I'm not including it because that's where they're equal, up until 6, because at 6 the area of A is greater than B. So, 4.85, not 4.45. 8. Okay, and then the last one says the maximum area of rectangle B. Well, I know that maximum area happened at 3.5, and the maximum area was 6.25. So the max area is 6.25 centimeters squared. 6.25 centimeters squared.